Hello guys, we are group 3 and today we are going to talk about the Laplace transform. What is Laplace transform? The Laplace transform is integral operator and another such transformation. Let f of t be a function on 0 to infinity. The Laplace transform of f is the function large f defined by the following integral. The domain of large f of s is all the values of s for which the integral exists. The Laplace transform of f is denoted by both large f and L of t. Let's see one example. Since f of t is defined by different formula on different intervals, we begin by breaking up the integral in the previous definition into 3 separate parts. Thus, the way of solving is as follows. Notice that the function f of t has jump discontinuities and when t equals to 5 and t equals to 10. These values are reflected in the exponential terms e to the negative 5x and e to the negative 10x that appear in the formula for large f of s. We will make this connection more precise when we discuss the unit step function. An important property of the Laplace transform is its linearity. That is, the Laplace transform L is linear operator. Let f of f1 and f2 be functions whose Laplace transforms exist for s is greater than alpha and let c be a constant. Then for s is greater than alpha, the followings work. There are functions for which the improper integral fails to converge for any value of s. For example, when the function f of t equals to 1 over t, which grows too fast near 0. Likewise, no Laplace transform exists for the function f of t equals to e to the t squared, which increases too rapidly as t goes to infinity. Fortunately, the set of functions for which the Laplace transform is defined includes many of the functions that arise in the applications involving linear differential equations. We now discuss some properties that will ensure the existence of the Laplace transform. A function f of t on the closed interval a to b is said to have a jump discontinuity as t0 is included in the open interval a to b if f of t is discontinuous at t0, but the one-sided limit exists as finite numbers. If the discontinuity occurs at an endpoint, a jump discontinuity occurs if the one-sided limit of f of t as t goes to a plus exists as a finite number. We can now define piecewise continuity as follows. A function that is piecewise continuous on finite interval is necessarily integrable over that interval. However, piecewise continuity on the closed interval 0 to infinity is not enough to guarantee the existence of the improper integral over the closed interval 0 to infinity. So, we need to consider the growth of the integrand for large t. A function f of t is said to be an exponential order alpha if there exist positive constants t and m such the following. You should become familiar with these since they are frequently encountered in solving linear differential equations with constant coefficients. The entries in the table can be derived from the definition of the Laplace transform. Using the definition of the Laplace transform that we talked about to get an explicit expression for L of f requires the evaluation of the improper integral. We have already seen how the linearity property of the transform can help relieve this burden. Then some further properties of the Laplace transform simplify its computation. These properties will also enable us to use the Laplace transform to solve initial value problems.
In these slides, we talk about inverse Laplace transform. As we learned Laplace transform before, we know that Laplace transform is a linear operator, and since it is a one-to-one transform, it must have an inverse transform. The inverse of Laplace transform is denoted by inverse Laplace transform of capital F of s, and it operates on capital F of s to transform it to little f of s. Basically, it means that if the function f is a continuous function of exponential order, and Laplace transform of the little f of s equal to capital F of s, then we can call that the function of little f of s is the inverse Laplace transform of capital F of s. And we also denote the formula to the inverse Laplace transform of capital F of s equal to little f of s. And there must be also condition. The condition is inverse Laplace transform exists if limit s to the infinity s over s squared plus 1 equal to 0.
Let's see an example of Laplace inverse problem. The problem is that find Laplace inverse of s plus 3 over s minus 2 squared plus 3 squared. This can be divided into two parts. One is Laplace inverse of s over s minus 2 squared plus 3 squared plus Laplace inverse of 3 over s minus 2 squared plus 3 squared. You know that Laplace inverse of s over s squared plus 1 is cosine t, and Laplace inverse 1 over s squared plus 1 is sine t, and Laplace inverse of 1 over s is et, e to the power of t. So the given equation equals to e to the power of 2t times cosine 3t plus e to the power of 2t times sine 3t. This is an example of solving a differential equation with using Laplace transform. The given equation is that y double prime plus y prime minus 2y equals t times e to the negative t when y0 equals 0 and y prime 0 equals 0. Using Laplace on both sides, then we can find the left hand side becomes s squared y plus sy minus 2y, and the right hand side becomes 1 over s plus 1 squared. Again, we can rewrite this equation as y equals 1 over s minus 1 times s plus 2 times s plus 1 squared. And using partial fraction, we can find the constants of each term. They are a becomes 1 over 27, and b becomes negative 1/3, and c is 11 over 54, and d is negative half. And then plug the constants back to the equation, we can find the Laplace inverse of the given equation. So yt equals 1 over 27 e to the t minus 1/3 e to the negative 2t plus 11 over 54 times e to the negative t minus 1/2 t times e to the negative t.
In this slide, we talk about unit step function. Unit step function is a piecewise function or a discontinuous function, and this is the idea is a way of modeling nicely when something is turned off and something becomes turned on at an instant of time. Let's see the picture right here. It shows that this is a discontinuity in graph at t equal a, and we take the value of unit step function to be 1 over 2 at point t equal a. And when t greater than a, the graph shows that the value is equal to 1. And when t smaller than a, the value of the unit step function is equal to 0. The rule basically is changed at when t or time is equal to some value a, so you can see the changes. And we also talk about residues theorem. Residues theorem is actually like a tool that helps us to solve the inverse Laplace transform which the function is discontinuous. And the most important part to know about residues is we need to know how to use residues function to solve the problem. And there's two things we need to know from the function is we need to know the value of the pole A and the value of n, which is depend on is simple, double or triple poles. Let's see the example in next slide. It helps us to understand more. So here's the example that we use residues theorem to solve inverse Laplace transform 1 over s times s plus 2. The first step, we need to find out the value of pole A. That means that we need to find out the point that is undefined in the function. So when s equals 0 and s plus 2 equals 0, we know that at point 0 and negative 2, that's undefined. So that's the value of the poles. And also there's two simple poles, so the n value is equal 1. And we plug it in the 0 into A, we solve the equation, we get 1 over 2, and then we plug it in negative 2 into the function, we solve out that the answer is equal negative 1 over 2 e to the negative 2t. So at the end we will know the answer of the inverse Laplace transform 1 over s times x plus 2 equal to 1 over 2 minus 1 over 2
Next, we're gonna talk about direct delta function. A direct delta function, the symbol is delta, is the derivation of unit step function. As we can see in the top graph, that is the graph of unit step function at t minus 0, and at the bottom is the we can see that is the when we take the derivation of the unit step function, we get the bottom graph, and that is the graph of direct delta function. Some properties of the direct delta function is that this function has a value of 0 anywhere except at that one point. Yet, if we take the integral of the direct delta function of any interval containing that one single point, it has a value of 1. And the direct delta function is used to model a sudden shock or a large force on a system. It's, for example, it's like forcing a function like a hammer striking an object or a short in electrical system. In this case, a large force or voltage will be exerted on the system over a very short time frame. Next, the direct delta function, when we use it with some function, it will give the function value at that point. For example, if we see the equation, if we take the direct delta of the ft, we get the value at fa. The Laplace transform of the direct delta function is, as we can see, is e minus to the power of minus as. To prove this, we use the definition of Laplace transform, that is the integral from 0 to infinity of the direct delta t minus a e to the power minus st dt, and we substitute direct delta with the derivation of unit step function. It becomes integral from 0 to infinity d dt of u minus t minus a e to the power e negative st dt, and as we can see, the dt cancels out. It becomes integral from 0 to infinity of e to the power negative st du t minus a. And we take the integration by parts. We use u as e to the power of negative st, and the dv is equals to du t minus a, and what we get is the e minus st u t minus a from 0 to infinity plus s, the integral from 0 to infinity of e to the power of negative st u t minus a dt. As we can see, the left limit is equals 0, because when we plug in infinity, the e minus st term is 0, goes to 0, but when we plug in 0 term, the u t minus a goes to 0 because it's lower than a. The u t minus a only has value when the t is larger than a, so it goes to 0, so we only have the right term. When we take the integral of the right term, we change the limit. Since it's u t minus a, we change the limit from 0 to infinity, becomes from a to infinity, so it becomes the s integral from a to infinity e to the power negative st, and it becomes negative e to the negative st from a to infinity. When we plug in the limit, it becomes e to the power of negative as. One example of direct delta function question is to solve y double prime plus 2y prime plus 2y equals to direct delta t minus phi. The initial condition is y0 equals 0 and y prime 0 is also equals 0. We can take the Laplace transform of both sides. On the left side, it's only s squared y plus 2sy plus 2y, because the initial condition is both 0. And on the right hand side, we take the Laplace of the direct delta. It becomes e to the power of negative phi s, and we take out y and move the s squared plus 2s plus 2 to the right hand side of the equation. It becomes y equals e to the power of pi negative pi s over s squared plus 2s plus 2. Then we factor out the s squared plus 2s plus 2 and make it in the form of s plus 1 squared plus 1. And as we can see, it is now in the form of, if we take the inverse Laplace, it's in the form of sine of omega t, and as you can see, the omega is 1, but the s is shifted by negative 1, so we add e to the power of negative t and then multiply it with sine t. But since there is a unit step function by minus pi, we also shift the t by minus pi, so the final solutions become e to the power of negative t minus phi sine t minus phi, and then unit step function of t minus phi. The next technique is to constructing differential equation from the solution. So what this is that the solution of the equation was given, but what we need to find is the original differential equation. And sometimes the question might ask for us to give a first order or a second order. And how to do this, the technique is to distribute S and then take the inverse Laplace, and then we can get the original equation after that. One easy example of the questions is find the first order differential equation with the solution in the form of 1 over s plus a times s plus b. So we set it as y equals 1 over s plus a, s plus b, and we can take either the s plus a or the s plus b term to the left side of the equation. And for this example, I take s plus a to the left side of the equation and multiply it with y. It becomes sy plus ay equals to 1 over s plus b. And then we take the inverse Laplace of both sides. It becomes y action plus ay equals to the e to the power of negative bt, and the initial condition is y0 equals 0, since there is no constant term on the left side of the equation. A harder example is to find the second order differential equation for a e to the power of negative at over s times s squared plus omega squared. So we set it up, y equals the ae to the power of negative at over s times s squared plus omega squared. Since the question asks for a second order differential equation, we have to bring the s squared plus omega squared to the left side of the equation so that we have s squared y. So what it becomes is s squared y plus omega squared y equals to a e to the power of negative at over s. And when we take the Laplace inverse of both sides, we get y double prime plus omega square y, and for the right hand side we can see that it's the inverse of unit step function, so it becomes a unit step function of t minus a, and the initial condition is y0 equals 0 and y prime 0 equals 0, since we don't have any constant term and a constant term times s on the left side of the equation.
Convolution theorem and periodic functions. Convolutions is an operator with following properties. First is commutative property. The second is distributive property. And third is associative property. And the last one is zero property. Theorem. If f of t and g of t are piecewise continuous on from 0 to infinity and of exponential order, then Laplace of f times g equals Laplace of f of t times Laplace of g of t equals capital F of s times capital G of s. It means that Laplace transform converts convolutions of function in time domain into simple multiplication in frequency domain. Proof. Capital F of s times capital G of s equals integral from 0 to infinity e to the negative s tau times f of tau times d tau times integral 0 to infinity e to the negative s v times g of v times dv. This equation equals to double integral from 0 to infinity e to the negative tau plus v times s times f of tau times g of v d tau dv. It also equals to integral from 0 to infinity f of tau d tau times integral 0 to infinity e to the negative tau plus v times s, g of v, and dv. Then substitute t equals tau plus v. Then the equation becomes integral from 0 to infinity f of tau d tau plus times integral 0 to infinity e to the negative ts g of t minus tau dv, which is equals to the integral from 0 to infinity integral tau to infinity e to the negative st times f of tau times g of t minus tau dt d tau. And the bottom part is the region, what we found. Proof: f times g equals integral from 0 to t f of t minus tau times g of tau d tau. Let t minus tau equals to the capital T, then f times g equals negative integral from t to 0 f of capital T times g of t minus capital T d capital T equals integral 0 to t g of t minus capital T times f of capital T d capital T, which is equal to g times f. Example: the problem is that calculate the convolution of the given function f of t equals t and g of t equals to e to the t. F times g equals to integral from 0 to t f of u times g of t minus u du, and equals to integral from 0 to t u times e to the t minus u du. Let v equals to t minus u, then dv equals to negative du. F times g equals negative integral from t to 0 t minus v times e to the v dv, and it is equal to integral from 0 to t minus v times e to the v dv. And this equation can be separated into two parts. One is integral from 0 to t times e to the v dv, and the other part is in negative integral from 0 to t v times e to the v dv. And solving the equation, f times g equals to e to the t minus 1.